So here are some problems. These are solved problems. I'll call these level 1 problems. I'll give a little bit more challenging problems in level 2. And so these are acid-base questions. First question is, what are the pKa's of those acids? So you should pause this, give it some thought, write some answers, and the answers that you should get are something like this. There should be pretty close to these, actually. And I just want to make a comment on the last one. You might think that the protons on the alkene they're going to be pKa of around 44, and the methyl group pKa is going to be around 50. But that methyl group pKa is going to be affected by the resonance in the conjugate base. So you take a proton from the methyl group, the CH3, and that carbanion is resonance stabilized, so that's going to be more acidic. Actually, the pK of that is around 43. And so when we take protons off, we're going to be taking protons off from both positions, both the alkene protons as well as the methyl protons, because those pKa's are similar. They're almost identical. And so, but either one of those is the correct answer. What are the Ka and Keq of the reaction of acetic acid with water? And so you should pause this, and here's the answer. pK is 5, so Ka is 10 to the minus 5. Keq is 10 to the minus 5 divided by 55. I'll point out here that I won't allow you to use calculators on exams. You'll have to set expressions up like this, and that will be fine for the answers. So the next question is the reaction of sulfonic acid. This is methane sulfonic acid with water favored to the right or left. First thing I want to say about this is assume that any sulfonic acid, something that has an SO3H, could have a methyl like here, could have a phenyl, could have something else. But assume this is a very strong acid, something like the pKa of HCl, which is minus 7. And so the answer to this is to the right. If the pKa is around 10, if pKa is around 7, then the Ka is 10 to the 7th. This is strongly favored to the right. Which conjugate base is more stable, the anion of the alkene or the alkane? And so you should say, oh, which one of these is going to be more acidic? That's going to be a more stable conjugate base. And the more acidic one is the alkene pKa of around 44 versus the alkane pKa around 50. So the next question is, which is more acidic? Let's have that come up. Which is more acidic, the alkene or with the chlorine or this fluoride? And so you should say, oh, the HF is going to be much more acidic. pK of around HF, it's a little less acidic than HCl. It doesn't matter what you choose as long as it's more acidic, rather less acidic than HCl. So it's actually pK of around 3. pK of around 3. But the alkene proton is going to be a pK of around 40. Might be a little more acidic because of the inductive effect of that chlorine, but it is not going to be a lot more acidic. So in any case, the HF is much more acidic. I put this problem here because lots of folks think you see the Cl and the F in one component and the F in the other, that the compound with the chlorine is going to be more acidic because HCl is more acidic than HF. No, that's comparing apples to oranges. Here we're looking at the element effect in a row. We're losing a proton from an alkene carbon versus a proton from a fluorine. And so much more acidic to the right. Draw the acid-base equilibrium of that in water. Again, you should be pausing these and drawing these out yourself. It doesn't help you to just watch these. You have to get used to drawing them out and knowing when you're right or when you're wrong. There it is. The next question is draw the arrows to show bond making and breaking and identify the acid, conjugate base, and conjugate acid. So there are the arrows. There are the different components, the names of the different components. For the above, write the Keq expression for the equilibrium and show how the expression for pKa is derived from it. So there's the Keq, which you've done before. Multiply both sides by water and you get the expression, you get this expression. And the concentration of water times Keq is defined as Ka, so that gives us this expression. And then we take the negative log of both sides, and that gives us this expression. And the negative log is defined as the pKa. So we've shown how the pKa was derived. And in the next question, at what pH are the acid and the conjugate base in equal amounts? That's going to be -2. is the KEQ greater than or less than 1 at pH of 0? And I'll stop right there and let you figure this out on your own. This is the last question in this series. Um, but in any case, at pH equals -2, since that's the pKa, the acid and the conjugate base are in equal amounts. And as we become less acidic, we decrease the H3O plus concentration. We shift the equilibrium to the right. So that means we have a lot more conjugate base than we do acid in this expression.